Okay, I think we'll go ahead and get started now. Can everyone hear me okay and see my screen okay?
Yes.
Okay. So I just wanted to put that simulation of air up on my screen for a minute. that you've been watching while you've been waiting. This is the ambient atmosphere all around us. It's in constant motion. This has actually slowed down 417 billion times, and this is air magnified at 0 degrees Celsius. And you can see it's in constant motion. The blue molecules that you see are nitrogen. The red molecules that you see are oxygen. And quickly rotating white and red that's coming right through the center of the screen right there and just faded away and coming across the screen, that's an actual water molecule, H2O. That represents the humidity in the ambient atmosphere. And the little yellow ones that you see floating around, very few of, that's the concentration of CO2, carbon dioxide, in the ambient atmosphere. So that's what the air around us looks like. It's in constant motion at all times. And that just leads me right into what we're going to go through today. An introduction to gas detection in the HVAC market space. And what we're going to go through, I'm going to tell you a little bit about our company, Odell HVAC Group, and the product that we represent, Armstrong Monitoring, the company that we represent. And then we'll get into why we use a gas detection system, how a gas detection system works, system design considerations, including sensor coverage, some common applications, and current codes and industry trends. So a little bit about Odell. We've been around for a long time, since 1987. We distribute just about every product that is available for the HVAC requirement in new build, design build, for the complete HVAC market space. And we carry some of the top brands in HVAC product line. And in a lot of cases, we are the exclusive distributor for that product within the Ontario marketplace. Armstrong has been manufacturing gas detection equipment since 1981. They were born and bred in Ottawa, Ontario. They are ISO 9001 registered. And they've kept that in place since 2015. All of their equipment is designed, manufactured, and produced right there in their Ottawa factory. So a great Canadian company, and we're proud to represent them and be their exclusive HVAC distributor in the Ontario marketplace. So now, why do we use a gas detection system with the HVAC system? For two reasons, and two reasons only. First and foremost, as a life safety system to protect people inside a building envelope wherever there's a possibility of toxic or asphyxiant gases building up inside that building envelope. We want to protect those people, so we utilize a gas detection system to monitor the concentration buildup. And when that concentration begins to build up, we will bring on the ventilation system so that we can dilute through ventilation. So dilution through ventilation. So basically a demand controlled ventilation system for the protection of people. Secondly, for protecting had my camera do a little reset on me there. I hope you can still hear me okay. Yes, so as I was saying, wherever there's a possibility of a combustible or explosive gas building up inside that building envelope, we want to monitor that concentration buildup through ventilation to bring those levels within that facility. And a spin-off to that, the extra added advantage is energy management. Controlling the ventilation system such that we don't have to run that ventilation system at maximum CFM 24/7. We can control it based on the gas detection system monitoring concentration buildup. And in so doing that, we're meeting not only regulatory compliance, but we are also taking advantage of energy savings and doing our part to protect the environment. So, how does a gas detection system work in general? We're all familiar with a thermostat. The thermostat that we have at probably a programmable thermostat that we have at home or in our office that keeps the temperature in the space comfortable, whether it's a very cold day in the wintertime or a very hot day in the summertime. That thermostat sitting on the wall, keeping everybody in that area nice and comfortable. And it does that with a little temperature sensor, a very small temperature sensor inside that thermostat is monitoring the ambient atmosphere in that room, in that envelope, and maintaining a temperature that keeps you comfortable. A gas detection system works similar to that. There is a sensor inside a gas detection transmitter, and that sensor could be any one of a number of different types that we'll go through in a minute. But that sensor element monitors the ambient atmosphere for any concentration of the target gas that it was designed and manufactured to detect. That information, that concentration level measurement information is sent back to a control point via constant communication. It's not just like that thermistor in that thermostat is monitoring in real time the temperature to keep you comfortable in the area that you're in a building. A gas detector is constantly monitoring the ambient atmosphere for any concentration of the target gas that it was designed to detect, and doing so in real time and transmitting that information in real time back to a control point. That control point is the device that is set up to perform an action based on the concentration of target gas that is being detected by that gas detector. And that typically what that control point is doing is bringing on the ventilation system so that you've got dilution through ventilation and you're maintaining safe levels of toxic or asphyxiant or combustible or flammable gas. That control point can be the manufacturer's, the gas detection system manufacturer's controller, or it can be a VFD or the building automation system or any other type of interface that you can set up to get the action that you want to take place once you detect a concentration of that target gas in the ambient atmosphere. The ventilation system itself can be controlled in any number of different ways. It can be a direct on-off. It can be a two-speed motor. It can be a VFD. It can be the building automation system that's controlling the ventilation system. And those ventilation components can be anything from a standard exhaust fan right up through direct outside air system or controlled fresh air dampers, um, any type of ventilation component that is set up to ventilate that space. The components of a gas detection system, so they consist of that little sensor element I was speaking of, that will detect the target gas, which is fitted into a transmitter. And the purpose of that transmitter is to amplify and reduce the noise on the very minute output out of that sensor element. Typically, a sensor element will output somewhere in the nanoamp range, like 10 or 20 nanoamps, which of course cannot be transmitted over a distance, over a long distance, over a pair of wires to control some type of ventilation component. So it has to be amplified and have the noise reduced on it so that it's a reliable and usable signal, something like a 4 to 20 milliamp, 0 to 10 volt, or some type of digital signal like Modbus or BACnet or Niagara that can be then transmitted over a long distance over wiring back to that control point, which again can be the gas detection system manufacturer's controller, or it can be directly to the building automation system, or in some cases, directly into a variable frequency drive or any other type of ventilation control component. Sensors commonly used in the gas detection industry include electrochemical, catalytic, infrared, solid state, and photoionization detectors. Electrochemical sensors are typically utilized to monitor toxic gases and asphyxiant gases, simply because they're very good at that. They've been developed for that, and they're very gas selective. So they're filled with an electrolyte. That electrolyte has its highest reactivity to the target gas that that sensor was designed to detect. So the electrolyte inside a nitrogen dioxide cell would be totally different than the electrolyte inside a carbon monoxide cell or a hydrogen sulfide cell or any other type of toxic gas sensor cell, because that electrolyte is chemically mixed to have its highest reactivity to the target gas it was designed to detect. Catalytic sensors migrated into the commercial and industrial gas detection space from the petrochemical industry, where they've been utilized for well over 50 years for monitoring combustible and explosive gases. They're very good at what they do. They're very sensitive, and they're very reliable at detecting combustible or explosive gases. Infrared sensors are based on infrared light. So there's a light source inside that sensor.
Morning.
Hi, this call is regarding an order placed under your name. To get more information,
infrared light source inside that sensor cell. And an infrared detector works on the premise that infrared energy will be absorbed by the carbon molecules in combustible or refrigerant gases or carbon dioxide. The amount of infrared energy that is absorbed versus the amount of infrared energy that was transmitted, that difference is taken down through an algorithm in the microprocessor and accurately tells you the concentration of the target gas you have in the ambient atmosphere. Solid state sensors have been around since the development of the transistor, because they're based on that same type of principle with the PN junction they utilized for a transistor, a wired surface mount component mount transistor. Those transistors, when they were developing them, they were trying to get more amplification on the current and voltage they could pass through them, and control that amount of amplification. Same way a solid state sensor works very similar in that it will detect the molecules of the target gas because they will displace the oxygen molecules on the sensor surface. And that causes a higher resistance, which causes more current to flow. And that current, that small current, again, taken back through that gas detection transmitter, amplified under microprocessor control, noise reduction, and turned into a signal that can be transmitted over a distance over a pair of wires. So again, 4 to 20 milliamps, 0 to 10 volt, Modbus or BACnet, some type of robust signal that can be transmitted for a distance to allow control of the ventilation system. Photoionization detector works on the premise of ultraviolet light. Ultraviolet light bulb inside that photoionization detector will ionize volatile organic compound molecules. So photoionization detectors are used primarily for the detection of VOCs. When those VOC molecules are ionized, they can be collected on a positive plate inside that little tiny sensor cell, which again upsets the resistance and causes more current to flow. And again, that minute current is amplified by the gas detection transmitter so that it can be transmitted over a distance to a control point for the ventilation system. Expressing the gas concentration values of various types of gases that we detect in the gas detection industry. Toxic gases typically measured in parts per million or parts per billion. That simply means that if you look at a building envelope, a container, if you will, that is 100 parts per million within that container. The ambient atmosphere inside that container represents 100 parts per million. In that atmosphere, there's 20.9% volume oxygen. 20.9% volume translated to parts per million is simply 20.9 as a percentage of 1 million parts per million, which is 209,000 parts per million. So the ambient oxygen inside that space, 209 parts per million, 209,000 parts per million. So monitoring toxic gas buildup, for instance, carbon monoxide, up to 25 ppm, nitrogen dioxide up to 0.5 to 0.7 ppm, various other toxic gases up to a very small parts per million, to bring on the ventilation and bring those levels back down to acceptable exposure limits based on ACGIH, NIOSH, and OSHA permissible exposure limits. Then there are the percent volume, just like the oxygen that I mentioned. So oxygen gases, asphyxiant gases, would be measured in percent volume, which is a direct correlation, as I just mentioned, to parts per million. Then there's combustible gases, combustible and flammable gases, and you'll hear LEL and LFL constantly interchanged because they're basically the same thing. Lower explosive limit or lower flammable limit. That is the concentration at which that gas has reached the point where, given the oxygen in the ambient atmosphere, if there is the introduction of a source of ignition, then you've got an explosion or a fire. So there is the lower explosive or lower flammable limit, and that goes all the way up to a concentration that is measured as the maximum upper explosion or flammable limit, UEL or UFL, at which above and beyond that, there's too much of that gas and not enough oxygen, so you're not going to have an explosion or a fire. But our concern inside a building envelope is not reaching the concentration of percent LEL. So, for instance, if we look at hydrogen gas is created during the process of charging lead acid batteries. That's one of the areas where hydrogen gas is of concern. When you're charging lead acid batteries, by their very nature, they are vented batteries, and they're vented because the charging process creates hydrogen gas. That hydrogen gas is much lighter than the ambient atmosphere. It will rise up towards the ceiling and pool there. The lighter molecules, even though I showed you the ambient atmosphere being in constant motion, the lighter molecules will eventually work their way to the highest point in that contained area or that building envelope. It is that pool, that buildup of hydrogen gas that we want to monitor. We do not want that pool to reach the concentration of 4% by volume or 40,000 ppm. That is the lower explosive limit or lower flammable limit for hydrogen gas. So typically we would bring on the ventilation at 10% of that lower explosive limit or lower flammable limit. So at 4,000 ppm, we would be bringing on the ventilation. To monitor hydrogen in particular, because there is a sensor for monitoring toxicity level hydrogen at 0 to 2000 ppm, to monitor for its combustible capabilities, you have to make sure that you are specifying or asking for a combustible concentration hydrogen sensing type element if you're monitoring for hydrogen in an area where you're charging lead acid batteries, because that goes up, like I said, to 40,000 ppm, and 10% of that, where we would typically bring on the ventilation, is 4,000 ppm. So those are the different ways that we measure the concentration of the target gases that we're looking for in the gas detection industry inside those building envelopes, so that we can enact the ventilation system and perform dilution through ventilation. When we're looking at system design considerations, there are a number of things that have to be taken into account. First and foremost, the application itself. In the HVAC industry, we know that there's only a finite number of different applications. Buildings are typically categorized by what type of facility it is. For instance, a logistics facility versus a warehouse facility versus a school versus an office tower. Knowing that application helps to understand the application itself. And when you understand the application, you can identify the target gases. For instance, in a recreation center, you're not going to be looking, the key gases you're looking, not going to be looking a recreation facility. They're typically going to have an ice arena and a swimming pool and some type of gymnasium or other sport facility within that recreation facility. So you're going to be identifying and monitoring different types of gases. For instance, in the swimming pool area, In the machinery room, you're typically going to be monitoring for any buildup of chlorine because they're constantly sanitizing the water in that pool through the use of chlorine. And if there's also a possibility that if they're sanitizing the water with chlorine, they may be taking it through a 100% aeration of CO2. CO2 at 100% concentration so that they can maintain the pH levels and keep the chloramines in the ambient atmosphere above the pool at safe levels so that people don't have that red rash and the red eyes and all of that. They do that 100% aeration with CO2 to maintain the pH level after it's the water's gone through that chlorine bath. So you're going to be sensing for buildup of CO2 as it is an asphyxiant gas, and you're going to be monitoring for any possible buildup of chlorine in that machinery room because the chlorine generator needs to be monitored versus a logistics center where the main gases of concern, carbon monoxide and nitrogen dioxide, from all the different vehicle activity within that facility and around that facility, including propane powered lift trucks and tow motors. The combustion of propane fuel also creates carbon monoxide and nitrogen dioxide. So as well as all the little delivery vans that are pulling in and pulling out, and the tractor trailers that are bringing the large loads of product into that logistics center, the tow motors as well can create high, nitrogen dioxide and carbon monoxide. And if they're using battery, lead acid battery powered tow motors and lift trucks, then they're going to have large charging bank areas. And again, the buildup of hydrogen gas, and you're going to want to monitor the hydrogen gas buildup and enact ventilation to make sure that gas stays at safe levels. Understanding the application and identifying the target gases helps to select the appropriate products for the target gases that you would find in those applications. Other considerations that come into play: how large is the facility? Because that will dictate the number of sensing elements required to provide adequate monitoring for that facility. A sensor will cover a finite area. If you look at, I'll draw an analogy here to an incandescent light bulb. If we take an incandescent light bulb and we put it in a wall fixture and put it on the wall, we get 180 degrees of light out of that light fixture. That's 50% efficiency. We take that same light bulb in that same wall fixture and we move it into the corner of the room and we get 90 degrees of light out of that light bulb. 25% efficiency. We take that same light bulb and put it in a ceiling fixture and move it towards the interior of the space we're trying to illuminate. We get 360 degrees of light out of that light bulb, 100% efficiency. Likewise with a gas sensor. A gas sensor works on the premise that natural diffusion and convection of the ambient atmosphere is taking place all around it, 360 degrees all around it. The amount of time it takes via gas laws and physics and gas dynamics for that gas to equal out over a 360 degrees radius of 40 to 47 feet for a occupational health and safety application is very quick. Very quick. In a matter of seconds, it will equal out over that type of an area. So if that sensor can see 360 degrees all the way around it, and if it given the fact that it has a radius of coverage for toxic gases of 40 to 47 feet, which is an area of 5,000 to 7,000 square feet. you can cover quite an area with a single sensor. But if that facility is much larger than 7,000 square feet, you're going to need a number of those sensors to be able to cover that facility. And just about every gas detection system manufacturer in today's world has that capability of monitoring multiple sensors with one controller and enacting ventilation based on those sensors reporting back in real time the concentration of the target gas within the area that the sensors are installed. Also, in regards to the number, how large the facility is, how the ventilation system is set up. Because typically in much larger facilities, there's a possibility that the ventilation system is set up such that it can be zoned. Also to take into account, is it a classified area? Has the electrical engineer having jurisdiction classified the area? If the area is classified hazardous, there are only two ways that you're going to be able to install electrical or electronic equipment in a hazardous area, an area that's been classified hazardous. Either intrinsically safe equipment or explosion-proof equipment. Intrinsically safe equipment, typically handheld devices. Portable radios for communication. Or portable wireless telecom type communicators for communication, or handheld gas detectors or any other type of handheld device moving around in that classified area are going to be manufactured and designed such that they meet the classification of being intrinsically safe. An intrinsically safe device gets that classification by way of the fact that it was designed as a very low current device. There is not enough current and enough voltage flowing through the electronics within that device to create a spark should any component or a battery be separated from the electronics. So there's no source of ignition. An explosion-proof device, on the other hand, is designed such that the electronics or electrical parts are encased in an explosion-proof housing, such that that source of ignition is encased in an explosion-proof housing, so that if any combustible gas seeps in or leaks in to come into contact with that electronics, which of course could be a source of ignition, then that housing will contain that explosion. Everything inside it will be destroyed, but at least your facility is still standing unharmed. So those are the only two ways you're going to get electrical or electronic equipment into a classified area. And typically gas detection and ventilation components are explosion-proof housings. In the case of fans, you're going to have spark-proof motors, which again are designed such that they will not generate a spark and therefore be a source of ignition. And again, how do you want to set up the ventilation system? What is the fan schedule? The sequence of operations you want to deploy in that particular design. And it can be any number of ways. Any number of ways, two-speed fan, VFDs that simply modulate the ventilation based on the demand required, or a simple on-off. That's what you would have in an area where you're charging lead-acid batteries. You typically wouldn't have that fan on. That fan would only come on if they were charging the batteries, and it can be controlled with a gas detector, such that you can set that gas detector to operate audible and visual notification appliances should that concentration rise faster than that fan can dilute it. So that's something to keep in mind. Is it a standalone system or monitored by a building management system or building automation system? When you're setting out to design a gas detection system, knowing as much as you can know up front and asking all the right questions allows you to have a design capability right from the beginning. Any electronic system in today's world can communicate to another electronic system. And it is a lot easier if you know from the start that that is part of your design consideration. So I go back to, I spent 25 years in wireless telecom. And one of the things coming up through that part of my career, I did a lot of system integration. And it was always first and foremost with the consulting engineers to write up a specification. If two systems were going to be interfaced, there was a system interface specification. Since I've joined the HVAC world 21 years ago, I've noticed that's something that has been sorely lacking in the HVAC world. There is no real thought given to system interface design specification. However, having said that, it's upon all of us to understand that that is whether or not that is a requirement moving towards the finished product. And any design, any system can talk to any other system. It depends on what you want to accomplish. It can be something as simple as having the gas detection system that fire alarm control panel so that when the firemen arrive on site and are looking at
Sorry,
that
Ron.
panel,
Just Connor from Odell here. You cut out. Can you just repeat your last sentence, please?
yeah, is my microphone cutting in and out?
I just did there. Yes. Yeah.
Oh, can you hear me now?
Yep. Yeah. Yeah.
Oh,
Sorry.
okay.
Maybe just
So,
restart.
any system can interface to any other system. And I was taking the example of an enclosed parking or underground parking garage, gas detection system for monitoring vehicle exhaust, carbon monoxide, nitrogen dioxide, interfacing to the fire alarm control panel. It can do that. It can send a contact closure, which most fire alarm control panels will accept as a supervisory signal, such that when the firemen show up on site, they know where the oxygen is coming from that's feeding that fire. The underground parking garage is probably the gas detection system has probably enacted the gas detection system, and of course, the ventilation fans are going and the motorized dampers are open, so there's a constant feed of oxygen. The firemen would like to know that, and they'd like to have the capability to turn that system off so it's not feeding oxygen to that fire. So knowing that you want two systems to interface at the completion of your project, talk about it up front. There are ways that that can be accomplished. But once the gas detection system or the other system that you want to interface to has been designed and is being installed, it's harder when you bring it up down the road. It's best to know right up front, right? And all the gas detection system manufacturers have some capability of providing that type of interface that you're going to be looking for. And then we got to take into account whether or not we're trying to install gas detection systems into a wet environment. Fire station. Fire station during the winter months, the inclement weather, they're going to be washing down those fire vehicles inside the firehouse. They're going to be spraying water all over the place. But at the same time, you've got CO and NO2 sensors in there that are monitoring the facility for buildup of vehicle exhaust. Knowing that you're going to be installing those devices into a firehouse, they can be provided with waterproof housings and splash guards that protect the sensor elements, because we all know that electronics and water don't play nice together. So knowing whether or not it's a wet environment, car washes, wastewater treatment centers, anywhere where it's a wet environment, knowing that you're going to be installing electronics into those areas, you can provide the appropriate type of housing to allow that to be accomplished safely. And expectations of extreme temperature. All of these food processing facilities that have opened up over the last 5 years or so, and continue to open up, that allow all these different companies that deliver meals to your door on a daily basis, or to various establishments that you go there and buy them. They've got kitchens that are generating heat and humidity. They've got flash freezers. They've got coolers where they keep all the produce. They've got entry and exit areas where vehicles are coming in, picking up these meals and leaving. So there's a possibility of all these extremes in temperatures. Knowing that, the system can be designed such that you take into account the expectation of extreme temperatures, and your system design is such that they do not come into play. So again, knowing these considerations up front really help with the design of the gas detection system. Sensor mounting heights. Sensor mounting heights in the gas detection industry for monitoring toxic gases. Those gases are toxic to human beings, not because human beings touch them, not because human beings walk on them, not because human beings can see them. Those gases are toxic to human beings because humans breathe those toxic gases into their lungs. And from their lungs, those gases get into their bloodstream, and from their bloodstream get into every organ in their body. That's what makes those gases toxic. And if you look at carbon monoxide and certain asphyxiant gases, when they breathe carbon monoxide into their lungs, carbon monoxide pushes the hemoglobin out of the bloodstream, and that hemoglobin is what takes an oxygen molecule to all your vital organs. So when that hemoglobin molecule is pushed out of the way by the carbon monoxide, you're robbing your blood of oxygen molecules. Therefore, you're robbing the rest of your body of oxygen molecules. And recent studies have shown long-term effects from exposure to low levels of carbon monoxide over a period of time. Health effects from carbon monoxide. Not to mention that at high concentrations, it is fatal. 1200 ppm. 1200 ppm of carbon monoxide, immediately dangerous to life and health. Your carbon monoxide alarm at home, your residential carbon monoxide alarm, monitors for 90 ppm. Monitors for a continuous reading of 90 ppm for 45 minutes before it goes into alarm. So we don't have all the false alarms that plagued the industry way back when they were first introduced. And mommy and daddy were freaking out and unplugging the thing and pulling the batteries out because mommy burnt the toast or daddy was boiling water. Today's residential carbon monoxide alarms have to see 90 ppm for 45 minutes before they start emitting an audible visual signal. Having been exposed to 90 ppm for 45 minutes, you already have a headache. You already feel like nauseous. You feel like you're getting the flu. But the beep, 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 and the little red LED starts flashing, and you immediately know you're being carbon monoxide poisoned. In the industrial and commercial space, carbon monoxide sensors monitor in ppm, 1 ppm right up to 200 ppm. Maximum allowable exposure to carbon monoxide in the workplace, 100 ppm. Allowable exposure to carbon monoxide in an 8-hour workday, 25 ppm. That's where we bring on the ventilation. We bring on the ventilation at 25 ppm to make sure that the carbon monoxide never rises above that. Nitrogen dioxide, the other constituent of internal combustion engine exhaust, because there is no such thing as 100% combustion. Nitrogen dioxide is created from the fact that the engine pulls in outside air to complete the combustion process because it needs the oxygen content. At the same time, it's drawing the nitrogen from the ambient atmosphere, and the incomplete combustion of nitrogen creates oxides of nitrogen. Oxides of nitrogen. And one of those oxides of nitrogen, NO2. One of them, oxide, the decimal 1, decimal 5, decimal 7. And we bring on the ventilation at decimal 7 ppm for nitrogen dioxide. Immediate danger to life for nitrogen dioxide, 13 ppm versus the 1200 ppm for carbon monoxide. 13 ppm, immediately dangerous to human health. So monitoring for those gases in the breathing zone, as well as all other toxic gases, monitoring in the breathing zone so that you can protect human beings by utilizing dilution through ventilation is critical. Area of coverage, typically for toxic gases, 5,000 to 7,000 square feet, depending upon how crowded the space is. If you're in a vehicle repair shop, it's not really that crowded. So you can stretch it out to 7,000 square feet, a radius of 47 feet. You get into a logistics center where maybe there's all kinds of racking and shelves filled with product and whatnot, and it's a little more cluttered, a little less free flow of the ambient atmosphere, the air inside that facility. You might want to bring that down to 5,000 square feet, which is a radius of 40 feet, because of all the clutter in the area, right? So gases that are heavier than air, combustible gases and refrigerants. You're going to monitor the pool buildup because they're going to migrate to the lowest area in the building envelope. So you want to monitor the concentration of that pool. You don't want that pool to build up with a combustible gas to the level at which it will create a problem, the lower explosive or lower flammable limit. You want to bring the ventilation on long before that. But having that sensor down that low, you do not want it right on the floor because you don't want it to be damaged by any liquids or water that will spill, and you don't want it damaged by any cleaning machinery that will be moving around. So you want to keep it about 6 to 10 inches above the finished floor. That will allow it to be safe and allow it to monitor the buildup of refrigerant or combustible or flammable gases in that area. And when it comes to those types of gases, if you're doing a chiller room, you're going to want a sensor at each and every chiller to monitor the compressor interconnect where it's typically the leak is going to occur. For combustible gases, depending upon the combustible gas, propane moves very slowly. So you may want to keep that down to 3,000 to 5,000 square feet, a radius of 31 to 40 feet. Methane, on the other hand, is very light. So you're going to monitor that up at the ceiling. And because it's very light, you can go with the 5,000 to 7,000 square feet. And again, you're monitoring for that pool buildup up at the ceiling. Sensor coverage, as I mentioned. In an underground parking garage, you can move that radius of coverage out to 50 feet simply because you're not monitoring to workplace health and safety concentration limits. Nobody works there. Nobody spends 15 minutes there. They come and park their car and they go up to their office or go up to their condo or up to their hotel room or up to the shopping mall, whatever the facility happens to be. So you can base those sensors out to a radius of 50 feet, which equates to an area of coverage of 7,850 feet. As I mentioned, in other areas that are workplace health and safety applications for toxic gases, you're going to keep that radius of coverage down to 5,000 to 7,000 square feet, a radius of 40 to 47 feet. And you can see in the little drawings at the bottom of that slide, both of those areas are adequately covered. The spaces outside of the circle, well, again, I'll draw the analogy to an incandescent light bulb. The light doesn't stop, right? And the ambient atmosphere doesn't stop moving in those situations. Yes, there is coverage out there. Is it as fast as the coverage right at the sensor? Well, a couple of seconds maybe. Because the ambient atmosphere, not only is it in constant motion on its own, but then there's all the extra added motion of people walking, doors opening and closing, vehicles moving. So there's a lot of different added motion to that air. So yeah, they're adequately covered. Gas detection systems for covering various types of facilities. All the different manufacturers provide them. We think we provide one of the best ones in the Ontario marketplace, and we can help you with your design. We can help you with sensor layout. We can show you how you can utilize the system to zone a facility, having sensors in a particular area, bringing on ventilation in that particular area. We can show you how you can communicate back to another type of system, whether it be a building automation system or a building management system or any other type of system. We can show you how you've got different types of outputs to activate different types of ventilation components, anything from ECM motor right up to a VFD, right up to a simple on and off type of ventilation fan. All of those different types of systems, we have access to them. We can show you how to set them up and design them. And we get involved in all the different applications you see on your screen right there, including ferries. There are some ferry movements on different areas of the Great Lakes where they're offshore communities, and they're not just moving people back and forth, they're moving vehicles, and they're also moving product back and forth. So wineries and breweries, warehouses, ice rinks, swimming pools, all of those different applications we get involved in on a regular basis. Now, I know we've come to the end of our time. I just want to quickly ask if anybody's got any questions that I can assist you with. Nobody. I guess I did my job very well today. Feel free to reach out to us at any given time. Anytime you've got any questions whatsoever, we're here to help you. And we have experts, not just myself, but any number of experts on our staff that can help you with anything to do with gas detection system, hydronics, or ventilation, or refrigerant. We are a resource here to help you. Feel free to reach out to us at any time. All right. I want to thank everybody for taking time out of their busy day to join us today, and hope that you have a great rest of the day. Thank you.
Thanks. Have a great day.
Thank you.